Have you ever wondered what makes carbon-based molecules so incredibly versatile, from dry cleaning solvents to cooking gas? The answer lies in covalent bonding, a powerful way atoms stick together by sharing electrons. Today we're exploring two non-polar covalent compounds, carbon tetrachloride and methane. Both contain carbon but they form bonds with different elements, chlorine in carbon tetrachloride and hydrogen in methane. Now, here's the chemistry behind it. A covalent bond is formed when atoms share one or more pairs of electrons, so they can each attain the electronic configuration of the nearest noble gas. Carbon has an atomic number 12 and an electronic configuration of 2, 4, meaning it needs 4 more electrons to complete its octet and become like neon, which has 2, 8. In carbon tetrachloride, carbon shares electrons with 4 chlorine atoms. In methane, it shares electrons with 4 hydrogen atoms. In both cases, carbon forms 4 single covalent bonds. Let's dive in and see how these structures form at the atomic level. Let's now take a closer look at the carbon tetrachloride molecule. Carbon has the electronic configuration 2, 4. It needs 4 more electrons to reach 2, 8, which is the configuration of neon. Chlorine has the configuration 2, 8, 7, needing just one more electron to complete its outer shell and become like argon, which is 2, 8, 8. So what happens? One carbon atom shares one electron each with 4 separate chlorine atoms, and each chlorine atom shares one of its own electrons with carbon. Through this mutual sharing, carbon achieves 8 electrons in its valence shell, and each chlorine gets its required 8th electron too. The result is a stable molecule, carbon tetrachloride, where one carbon atom is bonded to 4 chlorine atoms through 4 single covalent bonds. This molecule has a tetrahedral geometry, meaning the 4 chlorine atoms are arranged around the carbon atom symmetrically in 3-dimensional space. Let's now visualize the bonding in carbon tetrachloride using the electron-dot structure. Before bonding, carbon has 4 unpaired electrons, and each chlorine has 7 electrons in its outermost shell, one short of an octet. As bonding occurs, each chlorine shares one of its electrons with carbon. Carbon, in turn, shares one of its electrons with each chlorine atom. These shared pairs of electrons form covalent bonds. So in total, we have 4 shared pairs. That's 4 single covalent bonds. In the electron-dot diagram, we draw carbon in the center, with 4 chlorine atoms arranged around it. Between carbon and each chlorine, we place 2 dots representing a shared pair of electrons. Each chlorine ends up with 8 electrons around it, and carbon too has 8. That's a perfectly stable covalent structure. This tetrahedral molecule is used industrially, though with caution, as a solvent and in fire extinguishers. Now, let's switch to methane, the simplest organic molecule and a key component of natural gas. Again, we begin with carbon, configuration 2, 4, needing 4 more electrons to complete its octet. Hydrogen has the configuration 1. It needs just one more electron to be like helium, which has 2 electrons. So what does carbon do? It shares 1 electron each with 4 hydrogen atoms. Each hydrogen shares its single electron with carbon. This sharing creates 4 covalent bonds, one between carbon and each hydrogen. As a result, carbon now has 8 electrons in its outer shell, and each hydrogen has 2 electrons mimicking helium. The result is a stable methane molecule, chemical formula CH4 with a tetrahedral shape. Let's build methane using its electron-dot structure. Carbon starts with 4 valence electrons and each hydrogen has 1. Each hydrogen shares its electron with carbon and carbon shares one of its electrons in return. This forms a shared pair, a single covalent bond, between carbon and each hydrogen. So in total, we get 4 shared pairs of electrons or 4 single covalent bonds. In the diagram, we place carbon in the center with 4 hydrogen atoms around it. Between carbon and each hydrogen, we draw 2 dots, one from each atom, showing the shared electrons. The result is a stable structure where carbon has 8 electrons and each hydrogen has 2. This structure gives methane a symmetrical tetrahedral shape. Its bond angles are about 109.5 degrees. Methane is lightweight, clean burning, and widely used in households and industries as a fuel. Let's compare the two molecules we studied, carbon tetrachloride and methane. In both, carbon forms four single covalent bonds. In carbon tetrachloride, chemical formula CCl₄. Carbon shares one electron with each of four chlorine atoms. In methane, chemical formula CH₄. Carbon shares one electron with each of four hydrogen atoms. Chlorine with configuration 2, 8, 7 reaches 2, 8, 8 after bonding. Hydrogen with configuration 1 becomes like helium with 2 electrons. Both molecules are tetrahedral and nonpolar. However, their uses differ. Carbon tetrachloride is used as a solvent but is toxic and has environmental restrictions. Methane is a clean energy source used in cooking, heating, and electricity generation. Despite different elements, both molecules rely on the same fundamental principle, covalent bonding through electron sharing. So, let's recap what we've learned. Covalent bonds are formed when atoms share electrons to achieve stable configurations. Carbon, with four valence electrons, forms four single covalent bonds to complete its octet, whether with chlorine or with hydrogen. In carbon tetrachloride CCl₄, carbon bonds with four chlorine atoms. In methane CH₄, carbon bonds with four hydrogen atoms. We used electron-dot structures to see how shared pairs of electrons form these bonds. Both molecules are tetrahedral in shape, and each atom involved reaches the configuration of its nearest noble gas. I hope this session gave you a clear picture of how simple electron sharing leads to stable and useful molecules, ones we rely on every day. In the next video, we'll discuss the structure of covalent compounds formed by water and ammonia, two molecules vital for life and essential to chemistry. Don't miss it.